Hello, folks. We're here today to talk about the second part of gas laws. We're going to start with a little bit of refresher on the ideal gas law, talk about the kinetic molecular theory that allows us to apply the gas law, ideal gas law, and then look at some examples of stoichiometry using our ideal gas law instead of our 22.4 standard temperature and pressure value that we have been using. So as a refresher, our ideal gas law is PV equals nRT. So P is our pressure, and it can be in any of those pressure units that we've talked about in the past: atmospheres, millimeters of mercury, kilopascals. You just need to make sure that it's the same pressure as you use in your R value later. V is volume. It needs to be in liters. N is number of moles. You may have to convert to or from grams in a final problem. R is our universal gas constant, and it is going to vary based on what pressure unit you use. So just make sure whatever unit you are using for your pressure matches your unit up top and then in R. And finally, temperature needs to be in Kelvin. And remember that Kelvin conversion is to add 273 to any Celsius value. Okay, so last week we did this example of 5 moles of water at STP. Because it's at STP, we could just use a one-step molar conversion using that 22.4 that we've seen before. But just to show you how our ideal gas law is applied, we plug in 101.3 as our pressure, X, our volume is unknown, 5 is our number of moles, times the gas constant, times 273, that's 0 Celsius in Kelvin, our standard temperature. Plug it all in, we get 112 liters, we get the same value. And then the example that we led off with in class, find the volume of 85 grams of oxygen at 25 degrees Celsius and 104.5 kPa. So our R value is given, it's a constant, and that's the 8.314 based on kilopascals, the unit matching. So we want to write down our units and identify them. P is 104.5 kilopascals, volume is what we're finding. N was 84 grams, we have to convert it to moles with a one-step conversion. So 85 grams. And we are dividing by 32 grams because that is the molar mass of oxygen. We get that from our periodic table, 16 grams per oxygen atom. There are 2 of them. 2 times 16 is 32. So that's where the 2.656 came from. A one-step molar conversion, 2.656 moles of O2. Plug that in, simplify, solve for X, 63. Remember we were solving for volume, so liters is our unit. So with ideal gas law, we're going to use it towards the end of class as well today, but you want to make sure that your units match, you've done your conversions, and then just be careful with the algebra that's involved. So when we're talking about an ideal gas law, we're actually talking about something that doesn't exist. Real gases have a few more things going on with them, and so our ideal gas law is really a simplification. The real gas law is the formula in orange. We're not going to be using that formula, right? Big, kind of scary, so many variables. What's going on here? We don't have to worry about it. Instead, what we're going to do is we're going to talk about what an ideal gas is. We are going to make some assumptions and simplifications using our kinetic molecular theory and why we're allowed to apply that in our ideal gas. And last week we talked a little bit about what a theory is versus a law. So our theory is our well-tested explanation of phenomenon based on the observations of many scientists over time. Our laws are an observation based on that hypothesis, and typically in our case, they're going to have a mathematical component. So I can have a mathematical law that applies my kinetic molecular theory. So what are the assumptions we need to make in our KMT, our kinetic molecular theory, in order for our ideal gas law to be applicable? That's just our abbreviation. So assumption number one, the gases consist of a large number of atoms and or molecules that are in continuous random motion. So gas particles, lots of entropy, lots of energy, continually moving. Number two, the combined volume of all of the molecules of the gas is insignificant compared to the total volume in which the gas is contained. So gas molecules are spread very far apart. So in KMT, we're only counting the empty space. We are ignoring the size and the volume of the molecules themselves. Number three, the attractive and repulsive forces between gas molecules are negligible. So looking at the material of the container and the components inside the container, we could have forces of attraction due to those intermolecular forces we've talked about in previous units. So instead we're saying we're ignoring those, they do not exist. Number four, energy can be transferred between molecules during collisions, but as long as temperature remains constant, the average kinetic energy of the molecules does not change with time. So what we are saying is that as these molecules collide against each other, as they collide against the wall of the container, no energy is being lost. If you were to think about you running into a wall, you would have a lot of kinetic energy, you'd hit the wall, and all of that energy would be absorbed by the wall and you would stop. You would have lost that energy. It would have been transferred to the wall. Please don't run into a wall. Instead, what we're seeing with our gases is we are assuming that as these molecules bump against each other and as they hit the walls of the container, they're actually just bouncing back and keeping all of their energy. So we're saying that this is a closed system and no energy is lost with a collision. And assumption number five, the average kinetic energy of the molecules is proportional to the absolute temperature. We saw that back with our heating curves. More heat means more kinetic energy. And at a set temperature, the molecules of all gases have the same average kinetic energy. So in real life, molecules have different sizes and molar masses, and that is going to impact their velocity, but we're trying to negate that and say that no matter an element's composition, the kinetic energy is the same average in the container. So let's break a couple of these down and talk a little bit more about them. So our theory 2 talks about the overall volume. So again, just to reiterate, that the empty space between gas particles is so much bigger than the molecules themselves that the volume taken up by the molecules does not matter. So we're thinking, you know, we have one gas molecule and all the way over here is another gas molecule. Let's say this is our whole container. So we're saying that in the volume of all of this space, we can ignore the actual molecules because they're so tiny relative to the overall volume. We make that assumption for an ideal gas, but it's not true. Gases, remember, are made of atoms. They are matter. They do have mass and they do take up space. So even though an individual molecule is small, it does exist. Our third theory talks about the attractive and repulsive forces between a gas. So what we're trying to do is ignore intermolecular forces. So remember, we have LDFs, we have our dipole-dipole forces, and we have our hydrogen bonding. And those are all forces that can exist between molecules. So our London dispersion force for our nonpolar covalent gases, if you're polar covalent, you also have that permanent dipole. And then if you have oxygen, fluorine, or nitrogen with a hydrogen, you can also H bond. So when these compounds are in a gaseous state, they can form intermolecular forces and join together. So we're trying to ignore and negate those IMFs. So just think about a water molecule. Remember, polar, it can hydrogen bond. We have our negative oxygen and our positive hydrogens. So if steam was in a container, those positive hydrogens might interact with the negative oxygen of another molecule and form a hydrogen bond. And that would impact the energy that is available in the system. So we just have to ignore it. So all IMFs are being ignored in an ideal gas. And then our fifth theory item, just a little bit more about that, about the average kinetic energy. We're looking at an average of all the molecules, but some molecules actually have more energy and some have less. And when we're looking at kinetic energy, we are comparing mass and velocity. So two gases could have the same kinetic energy, but the one with the lower mass will move faster, and thus it will behave in a more ideal way. So let's look at all these theories and compare ideal to real gases. Right. So let's look at real versus ideal gases. What makes something act in a more ideal manner in order to give us better results in our calculations? So in real life, real gas molecules do have volume and they do attract one another. We have to account for those IMFs. So while a gas can never be truly ideal, some gases are more ideal than others if they meet one or more of the following conditions. So looking at our theories, we can apply them and see what makes something more ideal. So number one, having low pressure makes sure that there's more empty space between the molecules, so the impact of the volume of the molecules themselves is minimized. So a low pressure situation, a gas will behave more ideal. In a high temperature situation, you'll have more energy to overcome the intermolecular forces. As I said with that water molecule before, it might want a hydrogen bond, but at a high temperature, those hydrogen bonds are going to break and we can ignore them. The weaker forms of intermolecular forces, such as being nonpolar and only having an LDF, is going to make you more ideal. So oxygen gas is going to be more ideal than water, because oxygen gas is O2 and is nonpolar. It has that even sharing of electrons, and so it can only have London dispersion forces. And finally, a lower molecular mass has fewer electrons. So the smaller the gas molecule, the fewer electrons, the weaker those LDFs are. Think of the halogen series. Remember, fluorine and chlorine have relatively few electrons, so they're gases at room temperature. Bromine is a liquid and iodine is a solid. So as we add electrons, we increase the strength of our LDFs, and we want to minimize them for an ideal gas. So which gases then are most ideal? Our most ideal gases are going to be hydrogen and helium. The very small, very few electrons, equal sharing of electrons, low molecular mass. So all those pieces come together. Hydrogen and helium are the most ideal gases we have, but in absence of those gases, being at low pressure, high temperature will also make a gas behave in a more ideal manner. One other law that we need to talk about is Dalton's law of partial pressure. So Dalton, if we think back to Unit 3, was our father of modern atomic, the modern atomic model. He gave us back the idea of atoms. And he was really working almost as a meteorologist, looking at weather and the atmosphere. And he was looking at mixtures of gases. So he stated that the sum of the partial pressure of all the component gases in a mixture is equal to the total pressure of the mixture. So P total equals the individual sums of the mixture of gases. So the sum of the parts equals the whole. And then we can also think of this in terms of a fraction or a percentage. The partial pressure of one gas in the mixture is also proportional to the fraction of the moles of a gas it represents. So we can look at this as the total is 100%, and what fraction of that 100% is which gas. So a couple examples. Number one, a mixture of oxygen, carbon dioxide, and nitrogen has a total pressure of 0.97 atmospheres. What is the partial pressure of oxygen if the partial pressure of CO2 is 0.7 atmospheres and the partial pressure of nitrogen is 0.12 atmospheres? So the first thing to look at is make sure all of your pressure units are consistent. If they aren't, you have to convert until they're the same unit. But here they're all atmospheres and we're good to go. So our total pressure is 0.97, so we can substitute that in our equation. We don't know oxygen, so that's what we're going to solve for. And we know our other two gases are 0.7 and 0.12. Combine like terms and solve for the unknown. The partial pressure of oxygen is 0.15 atmospheres. Let's look at one more example. So a mixture of two gases has a pressure of 5.37 kPa with 1.5 moles of helium and 3 moles of hydrogen. Determine the partial pressure of each gas. So in this case, we can use our other formula. P1 equals X1 times PT, where X is the mole fraction. So we're not looking at a mole ratio like we do in a balanced equation in stoichiometry. We're looking at what fraction of the total is each gas. So in total, we have 4.5 moles, and 1.5 out of those 4.5 moles is helium. So there's my mole fraction, 1.5 out of 4.5 times the total pressure of 5.37 is 1.79 kilopascals. So we know there's only two gases in this container, so I could just subtract 5.37 minus 1.79, and that's going to give us the same answer of 3.58 kilopascals. The mole fraction accounts for what's left of that. Either way, mathematically is fine. It's actually kind of nice to calculate them individually, add them up, and see if your totals match at the end. A nice way of checking your answer. Okay, and our final topic today is gas stoichiometry at non-STP conditions. So back in Unit 8, we did stoichiometry. We looked at volume of a gas, but we specifically looked at STP 22.4 liters per mole. But we know that the ideal gas law is a better representation of what we see in our lab setting because we're not at STP. We're not always at standard temperature and pressure. So instead, we can use our ideal gas law and plug that into the equation instead of 22.4. It will change the overall answer, but is a better representation of what we're seeing in a specific scenario. So how do we solve our stoichiometry problems? Number one, start with a balanced equation. Number two, figure out what you are missing and what you need to know and what you have. So putting a question mark under the reactant or the product, write down the information you have, make sure you know what you're dealing with. Number three, make sure all your amounts are in moles, not grams. Number four, compare the molar amount using the mole ratio from the balanced equation. Solve for your unknown molar amount. And now, remember, moles is N, So you would have the substance that you need, you would know its moles, and you could plug it into the ideal gas law as needed. So here is the first problem. What volume of CO2 forms from 5.25 grams of calcium carbonate at 103 kilopascals and 25 degrees Celsius? So our balanced equation is as follows: CaCO3 plus CaO. CaCO3 yields CaO plus CO2. Already balanced, everything's a 1. 1 calcium, 1 carbon, 3 oxygens on either side. So we're being asked for volume of CO2, and we have been given grams of calcium carbonate. So in order to solve this problem, I can't use 22.4, but I'm going to start with a fence, and I'm going to go from grams of calcium carbonate to moles of calcium carbonate using my mole map to moles of CO2. And once I have moles of CO2, that will equal N, and I can plug that into my ideal gas law. So if you want to pause the video here and try and solve it yourself, I have the answer on the next slide. So I just want to give you a moment if you want to pause and try it yourself, that you can pause. Okay. All right, so here is our answer. I put R up at the top, just so we have it for later. So in order to do my molar conversion fence, I need to know the molar mass of calcium carbonate. So this is coming from the periodic table. Calcium 40.08, carbon 12.01, 3 times 16 for each oxygen is 100.09 grams per mole total. So I need moles of CO2 in order to use my ideal gas law. I can plug in each piece into my dimensional analysis fence. Grams of calcium carbonate will cancel. That's grams of a substance to moles of the substance using molar mass. So now I'm in moles of calcium carbonate. I bring that down. And then I can use my mole ratio, 1 mole of calcium carbonate for 1 mole of CO2. Plug all of that in, and I get 0.0525 moles of CO2. Once again, that is my N to plug into my ideal gas law equation. So PV equals nRT. Write down all the variables. It might seem a little tedious, but we have so many numbers and conversions going on. It'll make sure everything is where it needs to be. So 103 kilopascals, we are solving for volume. N is that 0.0525 moles. And then temperature, don't forget to convert that Celsius into Kelvin. A tricky step at the end, something simple and easy to overlook. Plug everything in and solve for volume, 1.26 liters. Okay. So let's try one other sample problem. How many grams of aluminum oxide are formed from 15 liters of oxygen at 97.3 kPa and 21 degrees Celsius? So in this case, our balanced equation, we have a mole ratio of 4 to 3 to 2. I'm not going to be using the aluminum at all. I don't need it for solving anything else in this problem. But I have been given 15 liters of O2, but I don't know how many grams of aluminum oxide I have. So since I have been given liters, I would normally use 22.4 moles per liter, or liters per mole, but I'm not at standard conditions. So instead, we have our balanced equation. We're going to use our ideal gas law, PV equals nRT. And we know pressure, we know volume, we know temperature. I will give you R, 8.314, but we don't know N. So we have to find N. And what that will give us then is moles of oxygen as our final answer for our fence. And we can plug in moles of oxygen and convert that with our mole ratio and molar mass to get to our aluminum oxide. So I'm going to pause here for a second, let you figure this out on your own if you want to give it a try, and then I will switch over to the key. All right, and our answers. So we're starting with our ideal gas law, so we can get to moles of oxygen. So our pressure is 97.3, our volume is 15.0 liters, our temperature is 294 Kelvin. We have to remember to convert that Celsius. So when I plug in my ideal gas law, N equals 0.597 moles, and we are still in oxygen. So now that I know moles of oxygen, I can get to grams of aluminum oxide using dimensional analysis, two-step fence. So moles of O2 can turn into moles of aluminum oxide using the mole ratio. So that is the 2/3. Moles of oxygen, top and bottom, now cancels. And from moles of aluminum oxide, we can go to grams of aluminum oxide using molar mass. I might just put the number up top. Again, that's coming from our periodic table. So 0.597 times 2 times 101.96. All the other units cancel. I get 121.74 grams of aluminum oxide, all divided by 3 from that mole ratio, 40.6 grams of aluminum oxide. All right. So when doing these problems, they are a little tricky. They are long. There's a lot of conversions involved. So my best advice for you is to always write your variables down, double check your units, being really careful, especially with temperature, and making sure that moles and grams aren't being confused, making sure your pressure is all in agreement. So all of those pieces, if they are there and you are working methodically, you should be able to solve those problems. All right, so that wraps up ideal gas law and stoichiometry. Thank you for joining in. Have a great day.